I would like to thank the organizer for giving me the opportunity to give this talk, and thank you all for staying to the end of this very nice conference. I'm going to tell you a simple story about the spin of the neutral excitation in fractional quantum Hall effect, and how it has been seen, I claim, without realizing as a missing state on a sphere. So the plan of my talk is to first review the fractional quantum Hall problem. Rather talking about fractional quantum Hall effect in general, I'm going to tell you about a particular aspect of it, and then how one can think about the neutral excitation, usually called Magnetoroton. And then I'm going to present you a numerical puzzle, missing state on a sphere, and how it is related to the spin of the neutral excitation. And the reference is this paper that Sung Nguyen and I put out in March this year. But when we talk about the fractional quantum Hall effect, usually we think about measurements of sigma xx and sigma xy, rho xx and rho xy. But I'm going to look at this problem from the theorist point of view. We have n particle in a magnetic field where the Hamiltonian is the sum of the kinetic term and the potential energy of all the particles. And if we have a correct hierarchy between scale, namely that the potential interaction energy is much less than the separation between Landau levels, we can do a projection to the Landau level, to say nth Landau level, and arrive to an effective Hamiltonian written in terms of non-commuting center of guiding center coordinates of the particle. So here, A and B's are the coordinates of the guiding center of the particle with index A, particle with index B. A and B runs from 1 to n, where n is the number of particles. And for a single particle, the coordinates x and y do not commute. To make this expression precise, we need to specify the ordering. And the way to order this is to go to momentum space. It turned out that this, so here the ordering is unique because of one can think about these exponents of R as a Taylor expansion. And the Fourier transform V tilde Q here is related to the Fourier transform of the microscopic interaction between the particle, smeared out by a Gaussian factor, and there is a factor that gives us the dependence on the Landau levels we project it to. Here, L of n is the Laguerre polynomial. What we have here is a quantum version of what in mathematics called the n-vortex problem. The n-vortex problem is a classical problem where we give a Hamiltonian, which is written as the sum of the potential energy between the particles. In the classical n-vortex problem, this potential is just a logarithm of R. That is, the potential is the same as the Coulomb potential in 2 dimensions. And one postulates Poisson brackets between the coordinates so that the coordinate x and coordinate y of the same particle do not commute. And the equation of motion are obtained by taking the time derivative of any variable to be the Poisson brackets of that variable with the Hamiltonian. So this gives rise to a deterministic classical system, which we have been studied for a long time. And the interest in this system is stimulated by a paper by Onsager in 1949, when he speculated that this might be relevant for turbulence, in particular for turbulence in 2 dimensions. Since it's a classical system, one can simulate it, and you can find beautiful pictures of the motions of these particles. So here is the picture that I took from this paper. It's a periodic orbit of 5 particles following the equation of motion that I give you on the previous transparency. This is somewhat a special solution because for more than 3 particles, the motion is chaotic. Both the quantum and the classical versions of the problem share the conservation laws. The conserved quantities are the number of particles, that's obvious. The dipole moments, that is the sum of the coordinates of all the particles. And the one component of the quadrupole moment, the diagonal components, the sum of coordinates squared of all the particles. And one can write down the commutation relation between the conserved quantities. And here you see the dipole moment, x in the x and the y direction do not commute. It commutes to the number of particles times the quantity that is the magnetic length square. And the commutator between the quadrupole moment and the dipole moment give us another components of the dipole moment. Some remark can be made just based on these conservation laws. From this conservation law, we see just mathematically a statement, trivial statement, that if you have a charged particle, it cannot move. It's like a fracton. It cannot have both momenta well-defined because px and py commute to the charge of that particle. So that includes quasi-Hall and quasi-electrons that Laplin introduced in the fractional quantum Hall effect. They have charge plus or minus 1/3. So only neutral quasi-particle can be associated with a dispersion relation. If we have an object that is neutral, it can move with a given momentum. But for the physics on the lowest Landau level, momentum is the same as a dipole moment. And the reason is that one can, if we rotate the dipole moment by 90 degrees and multiply it by LB, the magnetic length, to appropriate power, we can see that this object that we construct here commute with the coordinate in the same ways that momentum of coordinate would commute. That is, one can use it to build the translation operator. So the dipole moment is also generator of translation. And the quadrupole moment, similarly, is the generator of rotation. So here there is in this physics on the lowest Landau level, there is a very non-trivial interplay between dipole moments, momentum, quadrupole moments, and the rotation. So let's return to 1986. Gerwin, McDonald, and Platzmann translate the Feynman theory of superfluid helium to fractional quantum Hall effects. What they were interested at the time is the spectrum of the neutral, that is charge neutral excitation above, say, nu equal 1/3 quantum Hall state. The way they did that is to construct a certain variational trial wave function for such an excitation by taking the ground state and multiplied it by the operator of density at given momentum. When that density operator is already projected to the lowest Landau level. And by looking at the energy of that excitation, they get the dispersion relation of that excitation. There are certain approximation given that this in this calculation. We have to assume that it's basically the same kind of approximation that Feynman did in his superfluid work, except here that maybe we will see that near zero, while in Feynman's theory, it works better and better when the momentum goes to zero. In this calculation, it's not guaranteed that we get the correct state at q equal to 0. Another difference is that here the whole spectrum is gapped, while in Feynman's calculation for superfluid, we get the phonons at small q. It's called Magnetoroton because there is a characteristic minimum at non-zero value of q. numerical calculation, in particular direct diagonalization, largely confirm this kind of picture. So here is one. There are many of these pictures that one can get from the literature. The spectrum of excitation, I think here is on the torus. I forget how many particles, about 12 or 13 particles. Are the blue points correspond to the 12 or 13 particles. And you see a branch of excitation that can be associated with this magnetoroton with a minimum at non-zero value of k, and seems to go to a maximum at k equal to 0. But here there's one subtlety, one issue, one thing that one have to recall. So the magnetoroton at the minimum has some energy that's called delta of mr. And if I look at the energy 2 times mr, there is a whole continuum that is open. That is presumably the states that one can construct by taking 2 of these quasi-particles and then add the energy. So at k equal to 0, the magnetoroton goes to the continuum. And strictly speaking, we don't have a stable long-lived quasi-particle at k equal to 0 on the lowest Landau level with Coulomb interaction.
The colors?
The color corresponds to different values of particles, and I think this red color is something like the result of the single mode approximation. So the blue colors are the best numerics. 1/3. What at 1/3?
1/3.
Yeah, at 1/3. Okay, so Joliker in 2017 made a interesting discovery that I think hasn't been followed up numerically. That he said that if one take the nu equals 7/3, that is a quantum Hall state on the not on the lowest Landau level, but on the next Landau level, and assume that we have a white well. White well simply means that one replaces the Coulomb interaction with some interaction that is more smooth at r equal to 0. Then one can achieve a situation in which the magnetoroton, instead of going to a maximum, local maximum at k equal to 0, go down and goes to a minimum, a local minimum. So here, the important thing is, another important thing is that it's below the continuum. And so that quasi-particle in principle cannot decay, because 2 quasi-particles would always have energy that is larger than the energy of that particle. So k equal to 0 mode is a stable quasi-particle. So here, what is interesting is that we have a low energy mode that can be long wavelength, and we can try to understand the properties of that long wavelength and low energy mode. This is a picture that Jolicoeur obtained on the torus. On the torus, the momentum is discrete, but one can see that all modes can be reproduced. All possible values of the momentum, including momentum k equal to 0, we have a mode, this is a ground state, and there is the first excited state at k equal to 0 correspond to some, we can see that k equal to 0 excitation. The calculation also was done on the sphere. So if we put the quantum Hall effect on the sphere, instead of linear momentum, we have angular momentum. So the plot here would be the energy spectrum as a function of the angular momentum. The ground state have 0 angular momentum. So here is the ground state, and here is some excited state. And here there is a branch that looks like, vaguely like a magnetoroton. Let's go like 6 down to L equal to 2. But then what was observed is that there is no continuation for L equal to 1 and L equal to 0. There's missing L equal to 1 mode, and there is a missing L equal to 0, it looks like. Sorry? Yeah. Yeah, so I'm going to tell you that story. Yeah. Yeah. So where are the L equal 1 and L equals 0 mode? And are they absence are due, as the author Joliker due to us, due to finite size effect. And we will see that the absence of this mode has a more fundamental reason. It's not because we have a finite number of particles or the sphere radius is finite, but there is a reason for that.
They're present for U equals for the lowest Landau level.
It is lowest Landau level is field. There's next Landau level. It's all single Landau, but in the approximation, basically, it's just a calculation with some potential V that is some function multiplied to the Laguerre polynomial corresponding to the next Landau level. At a single Landau level, and there is a missing mode on this Landau level. Two missing modes. And let's try to think about this problem, not in terms of the electron, but in terms of the quasi-particles. So here, if we believe the result on the torus, near k equal to 0, we have some stable quasi-particle, and we should be able to describe the long wavelength regimes by writing down the effective Hamiltonian describing this quasi-particle. Imagine that the sphere is very large. Then we can write down the Hamiltonian as the gap plus k squared divided by 2m, and quantum mechanics dictates that we replace k squared by h bar times time derivative. And we know that the Laplace operator on the sphere has eigenvalue L plus 1, and L can run 0 to 1 to 2. Long wavelength corresponds to small l. It appears that this expression should work better and better if we go to small and smaller l. And so if this calculation is the whole story, then the L equal to 0 or L equal to 1 mode should not be missing. It should actually be more robust. This calculation become less and less reliable at larger and larger L, not at smaller and smaller L. But this calculation, this argument ignores one possibility, and that is the possibility that the quasi-particle may carry a spin. And here let's pause and then talk what we mean by spin. A quasi-particle with a zero, here we have a particle with zero momentum. And zero momentum means that just spin is just the total angular momentum of this particle, because x times p, the orbital momentum is equal to 0. You have to think about this as an expression that written for the quasi-particle. Of course, at the level of the electrons, everything is in the orbital momentum. On the electrons already completely polarized. The angular momentum of the electron enter both here and here. But from the point of view of the quasi-particle, its spin is equal to its total angular momentum at p equal to 0. What is the effect of the spin of the quasi-particle on the spectrum on the sphere? Now, there are two. There's an intuitive way about to think about this problem. If we have a particle on a sphere, imagine that its spin is perpendicular to the surface of the sphere. When it moves along the sphere, the direction of the spin changes. And we know that if we have a spin and we change its direction, there is a Berry phase proportional to the area of the solid angle of the area of the region on the sphere. Another way to think about the same, to say the same word, but not relying on the extrinsic geometry, but only on the intrinsic properties of the sphere, is to say that a quasi-particle with spin coupled to the spin connection of our space. So instead of di, you have to replace di plus I times s times omega I, where this omega I is the spin connection of the two-dimensional space. And that means that these particles move in an effective magnetic field. And the magnetic field is proportional to, in this picture, is the same as a magnetic field of a magnetic monopole in the center of the sphere. And by doing the very careful with the factor of 2, we find that the magnetic monopole charge is equal to 2s times the charge of the monopole, of the minimum charge of the monopole at the center. Or in some unit, magnetic monopole charge is equal to s, where s is the spin of the particle. Such an effect doesn't appear on the torus. When we have a particle on the torus, the spin connection can, the torus Euler characteristics of the torus is equal to 0. And so this quasi-particle basically move as if it is in the, on a flat space. Then we can, now we have a problem of a particle moving, instead of a particle with spin moving on a sphere, we have a charged particle, equivalent particle, problem of a charged particle moving on a sphere. And this problem has been solved by Wu and Yang when they are thinking about the Schrödinger equation in the field of a magnetic monopole. In particular, if we read the article, we find that the allowed value of the angular momentum of a particle in the field of the magnetic monopole parameterized by quantum number L and M, where L runs not from 0 to infinity as usually, but runs only from the values of the magnetic monopole charge to infinity, Q, Q plus 1, Q plus 2, etc., where M still runs from minus L to plus L. So magnetic monopoles preserve rotational invariance. All the spherical harmonics are still representation of the rotational group, but the allowed representation have L that run not from 0 to infinity, but some values of L's are forbidden. So that is the resolution of the puzzle of the missing state. The L runs from S to infinity. The absence of the mode with L equal to 0, L equal to 1 implies that S has to be equal to 2. So the magnetoroton at k equal to 0 has been seen in these numerics as a spin 2 quasi-particle. So another set of remarks. In various variational construction of the spherical excited state, the absence of L equals 0, L equal 1 mode have also been seen. And people try to write down some plausible wave functions for excited state above the Laplace ground wave function on a sphere. Usually there is one can see that it's very difficult to write, but the ansatz would give us something that is 0 when L equal to 0 and L equal to 1. And this finding is consistent with the exact diagonalization result that I showed you before. On the other hand, on a torus, doing exact diagonalization, we find all value of k, including k equal to 0, k equal to plus or minus the minimal value of k on the torus. Sometimes the variational ansatz have trouble coming up with these modes, k equal to 0 or k equal to 2 pi over Lx. But these modes exist in exact diagonalization. Another thing is that this spin 2 nature of the k equal to 0 magnetoroton is not something very new. It was suggested essentially by Haldane in 2 papers around 2009, 2011, and elaborated later by various other people. Yeah.
On the torus, say like a square torus, can you check the quantum number on the 90-degree rotation?
I don't know if they have checked this quantum number. I don't think. Yeah. Yeah, that's something that should be checked. Okay, so in the last few minutes, I'm going to tell you how to find the spin of this, determine the spin of this mode using polarized Raman scattering. So we can excite this mode by, the way this mode is excited in gallium arsenide is to use photons, so laser. So we shine laser to this sample and then observe the photons that are coming out with slightly smaller energy than the incoming photon. The difference between the energy of the incoming and the outgoing photon is the energy of the excitation that is left on the system. By using photons that carries spin, so recall that the spin of the photon can be +1 or -1, we can determine also whether the things that is left on the sample has angular momentum 0, +2, or -2. So that experiment has been performed by Lin Jie-du group in Nanjing University. So the setup of the experiment is the same as one that we proposed. We fixed the polarization, the circular polarization of the incoming outgoing light. So there are four possibilities depending on the polarization of incoming and outgoing photons. And there's one peak that appears only in one of these four possibilities. So this peak corresponds to the excitation on the sample having angular momentum in this convention s equal to -2. It's consistent with the theoretical argument that I have just given you.
7/3.
That is within the 1/3 state. It's not 7/3. It's within 1/3 and a 2/3 state. In the 2/3 state, they see a flip, a value of s that is different from 2 by sign. I think they also do 2/5 and then confirm that it has the same. So one can ask, well, why in experiments one managed to measure a mode that in principle, at least formally, should not exist. It is in the continuum. I guess the answer here is that this mode still exists. It might have an intrinsic width. It can decay, but the decay width of that mode presumably is smaller than its energy and still can be seen. Experiment. So how does one understand the spin of this? So there is an old paper by Shouchen Zhang in 1992, when there is a mysterious set of pictures of how one could understand different regime of the magnetorotons. At large momentum, one can think about the magnetoroton as a set of two quasi-particles carrying one quasi-particle and one quasi-hole. And they are very well separated from each other. The dipole moment is very large, which corresponds to very large momentum. When we go to smaller momentum near the minimum, for example, the dipole moment should shrink, and the size of the dipole becomes smaller. But as we go further to k equal to 0, Shouchen argued that we should see an object that has no dipole moment. So we draw this kind of picture. It should be two quasi-particle, two quasi-hole. But I think the picture more likely, I think at least when I was thinking about this, it should be slightly different. How many minutes? How much time do I have?
5 minutes.
Okay. Okay. So let's think about this mode using the language of particle physics. In particle physics, we can get information about the charge distribution of a particle by thinking by measuring the charge, so-called charge form factor. We can also introduce the notion of the charge form factor for the magnetoroton in exactly the same way. So here is the expression. I take the density at coordinate equal to 0. There is no reason why I should take this coordinate to be different from 0. There's just some simple exponents, some simple phase factor that I get if this coordinate is not 0. And sandwich it. So this is a projected density at x equal to 0, and sandwich it between two single particle states. One single particle state with momentum p and another single particle state here with momentum p prime. If these states, if p and p prime are exactly are very stable particles that cannot decay, these are just an eigenstate of the Hamiltonian. So this is a complicated many-body object that has that can be interpreted as giving us the information about the structure of our quasi-particle. So here we can go to the center of mass momentum, p plus p prime over 2. I call that capital P, p prime minus p is q. So q is usually called the transfer momentum. In the experiment, this is the momentum that is transferred from the photon to our quasi-particle. So okay, here, so from symmetry, I think one can deduce that this F has to be 0. It is basically a total charge of the particle. It has to be, for Magnetoroton, it has to be 0. This part has to be, this is basically the dipole moment. It has to be equal to P. And this one has to be, give us the information about the spin of the particle. So this F is equal to the spin. The Fij should be the second. This is basically the quadrupole moment of the particle has to be equal to S. Since the spin is the same as quadrupole moment on the lowest Landau level, an object with spin should have charge, say, plus inside or minus inside or the other way around. Depending on the feeding factor of the quantum Hall effect, we should have a picture that looks more like this. Let me skip this and go to the conclusion. So some fractional quantum Hall system have spin 2 quasi-particles. And this fact explains the missing state on a sphere, which is the state that exists on the torus but do not exist on the sphere. And this mode can be seen by a polarized Raman scattering. Thank you very much.
But so what is the role of the first excited Landau level?
The role is to lower the, to change the dispersion relation. It seems that on the next Landau level, the dispersion relation at k equal to 0 is softened. And so for a reason that I have some speculation why it happened, but the mode at k equal to 0 becomes stable. That makes it very well defined. It's very well, can be seen in numerics because it's separated from all the other things. So on the sphere, you can also see this mode separated. Well, at L equal to 2, for example, it's separated from all the continuum.
It just merges with the continuum. It's hard to tell that there's.
Yeah, on the numerically, it's make it easy that mode's well defined and detectable.
You have this cartoon for Magnetoroton, the very symmetric one. How do I know that it's L equal to 2? Is there some phase winding? It's like when you compare it to Zhang's picture and like the last slide or something.
So Zhang's picture doesn't, seems to have this object drawn here has 0 both, it has 0 diagonal quadrupole moment. If I take integral of rho times dx, so sum of the quadrupole moments of all these particles come to 0. But we know that the spin on the lowest Landau level is the same as the quadrupole moment. So I take the liberty to modify this picture.
In the experiment you described, what is the momentum of the particle on screen? Is it really
Momentum 0, basically, because when you have photons coming in, it's momentum. So its momentum is equal to 0, basically. I don't know how. Yeah, its momentum is equal to 0.
Is the spin of the quasi-particle only well-defined at k equals 0, or does it make sense for the entire branch?
It's that's why I was trying to introduce the notion of the form factor. This form factor is well defined everywhere. So this coefficient go somehow. Yeah, this function f2 of ij should be well defined for all values of p, but it's a function of momentum. At p equal to 0, it becomes a delta ij times the spin.
Use this to like figure out what the spin is for the models where the k equals 0 is kind of in the continuum. Maybe you can't access it.
But k equal to 0 in the continuum, then it's becomes less. This one cannot strictly define this matrix element. So I can't use it anymore.
Is there a sense in which the spin of this quasi-particle is universal information? It always has to be the same value? Or if...
So there is in order to do that, one have to assume that there is a way to change the parameter of the interaction without changing the state to lower this. So in the case we have seen in this case of the quantum Hall state, the new quantum, one can lower this mode at k equal to 0 to separate from the mode from the continuum. I don't think I can make the following statement. I can make the statement that there is a sum rule. Let me show you a sum rule. A sum rule here is a sum rule. These two functions, rho of omega and rho bar of omegas, are the graviton absorption cross section. This graviton absorption rate at momentum omega bar at 2 omega, but the polarization of the gravitons are opposite of each other. The quantity on the right is a property of the topological state, that is with angular momentum. So it's a shift, and so it doesn't change for continuous change of parameter. In order to make the statement about the spin of the quasi-particle, I have to make an additional assumption that this sum rule is dominated by one mode.
Sorry, is that integrated over all q, or is that q?
Integrated over it's q equal to 0. It's q equal to 0.
Okay, maybe one last question.
Is there a chance that there can also be excitations with total spin 2 with other projection? Because this one has total spin 2 and like projection equal to 2, and like as equal to 2. Is it possible to have excitations with as equal to, let's say, 1 and as total equal to 2? Or they will be
Well,
like...
the magnetic field breaks the rotation. So there is only rotation around the z-axis. There is no total angular momentum. It's two-dimensional system.
Right. I think that brings the workshop to an end. So let's thank all the speakers and your